Let's use an example to illustrate how we would find the inverse of a function. Now, in order for an inverse function to exist, the function has to be one-to-one. But if you find a problem that says find f inverse of x, if f of x is equal to, and then it has some algebraic expression, you can go ahead and assume that that function is one-to-one and that the inverse exists. I think it would be a misleading question to say find the inverse of a function for which the inverse doesn't exist. If you wanted to be super careful, you could verify that the function that you're finding the inverse of is one-to-one by sketching a graph using a graphing utility such as Desmos, or perhaps a graphing calculator. But I will go ahead and assume that this is a one-to-one function. After you verify or assume that it's a one-to-one function, we will set this equal to y and we'll solve for x. The reasoning for this is relatively straightforward. If we start out with f of x equals y, then if we solve for x, we'll have something here involving y. Let's call it g of y. G will be the inverse. Remember, that's what it means to be an inverse. The x's and y's are switched, and that's exactly what we have over here on the star. So we'll go ahead and solve for x, and I would like to remark that frequently this is the most challenging part of the problem, especially when you have something on the left-hand side that looks like what I've put in parentheses. So in order to solve this 2x minus 1 over x plus 3 equals y, there are a few steps to follow. The goal of these steps is to get everything with an x on one side and anything without an x on the other. So the first thing I'm going to do is I'm going to multiply both sides by x plus 3. So I get x plus 3 times 2x minus 1 over x plus 3 equals y times x plus 3. And what I'm doing here is I'm multiplying by the denominator. So the x plus 3's will cancel, and the next thing I'll do is I'll distribute this y. So 2x minus 1 equals yx plus 3y. Now, any term that has an x, I'm going to move to one side, and anything without an x, I'll move to the other. It doesn't matter what side you move each to, as long as they're separated. So I'm going to go ahead and subtract yx to remove this yx term from the right-hand side, and I'm going to add 1 to both sides to remove this term that doesn't have an x from the left-hand side. So what results is I get 2x minus yx equals 3y plus 1. From here, we can factor an x out of both terms from the left-hand side, and what that will result in is x times 2 minus y equals, and we won't do anything to the right-hand side. We'll just leave it as 3y plus 1. Then finally, we'll divide by 2 minus y, and we'll get x equals 3y plus 1 over 2 minus y. Now, depending on the problem, this may be easier or harder. To give you an idea of what I mean, suppose you had the function f of x, which is 3x minus 1. If you wanted to find the inverse of this function, you would set 3x minus 1 equal to y, solve for x. Well, to solve for x, all you have to do is add 1 and then subtract 3. So you get that x is y plus 1 over 3. Contrast that to this problem where the steps to solving for x were, well, let's say, more numerous. In any case, the second step is to solve for x, and then the last step is to switch all the x's and y's. So everywhere you see an x, put a y. Everywhere you see a y, put an x. And what results will be the inverse function. Notice in this little mini example to the right, the result would be that the inverse function, f inverse of x, is equal to x plus 1 divided by 3. So to briefly summarize, we set f of x equal to y, solve for x, and we switch y and x.